Welcome to lecture 7 part 1 state machine design. Here we'll discuss about how the flip-flop can be used as frequency division circuit and designing counter circuit. Afterwards we'll design the signal flow graph from the counter, and later on we'll design the state machine using the flip-flop. Okay, so this is a review slide from the previous lecture, the counter lecture 6. So you have seen this is a 2 flip-flop, means 2-bit counter. As the clock is defined, this is asynchronous counter. So this is basically 2-bit asynchronous counter. Main concept is here we are using the flip-flop as a frequency divider circuit and also as for designing the counter. Now first look at here how it can be used as a frequency division circuit. Like if you connect the J and K of the first flip-flop and JV KB of the second flip-flop with 1. So look at here 1, and your initial clock is here, and the output of the first flip-flop is used as a clock of the second flip-flop. If you connect such a way, then your JK flip-flop will work as a T flip-flop or toggle flip-flop, and this will work as a counter. This will act as a counter actually. So and one more thing is, like here, if your frequency here is your FC, here your frequency will be FC by 2, here your frequency will be FC by 4. This part we already discussed actually, why it is FC by 2 by 4. If it is not clear to you, I suggest you review the counter lecture, right? Okay, so this concept will be needed here. So just look at here, this is actually 3 flip-flop, that means it will produce 3-bit counter. So you already know for 3-bit it will have 2 to the power 3 8 state, and it will count 0 to 2 to the power 3 minus 1. That means 8 minus 1 7, 0 to 7. So it will count 0 to 7 1 on 1, then it will again go back to 0 and again going to 0 0 0 0 1 and keep going. Okay, so now here this is your Q naught, right? And this is your clock. So this is your primary clock or input clock, you can say. So this is your clock, and the output of Q0, this is acting as a clock for the Q1, and the output of this one, the second flip-flop, will be counting as a clock at third flip-flop, right? Just look at here. So this is your input clock and Q0. So if you look at the period here, so period is double for Q0. That means frequency is becoming half here. For Q1 it becomes double of this one, TQ2. That means frequency is getting half here, right? But frequency is 1/4 of the primary one, and for the last one frequency is 1/8 of primary one, right? So if you keep going this way, for 4-bit 1/16. Okay, so this concept is actually discussed here. First, the frequency division. So what we already discussed, like if we connect the flip-flop J and K input with high or level 1, then it will change the state, or it will toggle whenever the signal on its clock input goes from high to low, if we consider is a negative edge triggered. Okay, and Q0 is connected to the clock input of Q1, so Q1 is connected to the clock of Q2. And to remember a couple of things, the flip-flop Q not toggles on the negative transition of input clock. Thus, the Q naught output waveform has a frequency that is exactly 1/2 of the clock pulse frequency, what we already discussed. So, after first flip-flop, it will be half, second flip-flop 1/4, third flip-flop 1/8, fourth flip-flop 1/16, right? So it is saying, so after second it will be 1/4, and after third it will be 1/8, right? Which basically means each flip-flop output is a square wave, which means it has 50% duty cycle. Okay, this is very important. So we already saw actually if the flip-flop can be used as a frequency division circuit. So we can get some general equation from there, just like as described. Each flip-flop divides the frequency of its input by 2. Thus, if we are to add a fourth flip-flop to the chain, it would have a frequency equal to 1/6 to the clock frequency, and so on. So using the appropriate number of flip-flop, this circuit could divide a frequency by any power of 2. So specifically using n flip-flop, it will produce output frequency from the last flip-flop, which is equal to 1 to the power n of the input frequency. Okay, so input frequency divided by 2 to the power n. So it will give you the number of division frequency. So you already know, so it can be used as a frequency division, right? The flip-flop. So the many applications require frequency division. For example, your wristwatch is no doubt a quartz watch. The term quartz watch means that a quartz crystal is used to generate a very stable oscillator frequency. The natural resonant frequency of the quartz crystal in your watch is likely 1 MHz or more. In order to advance the seconds display once every second, the oscillator frequency is divided by a value that will produce a very stable and accurate 1 Hz output frequency. So there is one more application of the flip-flop, which is counter, which we already discussed in the last lecture, right? The sequence of state of flip-flop after occurrence of each clock pulse. So after changing the clock, or after each of the clock pulse, the sequence will change, right? So let the value represents a binary number where q2 is the to the power 2 position, q1 to the power 1, q0 to the power 0 position. The first 8 q0, q1, q2 state in the table should be recognized as the binary counting sequence from 000 to 111. So what it suggests, just look at table for 3 input counter or flip-flop actually. So what it says here, so if we have 3 bit, that means 3 flip-flop to the power 3 8, so it will count 000 to 111. So in that case, after first clock edge, it could be positive or negative. Here it is negative edge clock. So after first it will be 001, and your q0, q1, q2 will be 0 0 0, least significant, most significant. After second it will be 010, right? After third pulse it will be 011. After fourth it will be 100. Okay, so it will keep going up to 7. So after 7 it will be 111, and later on after 8, so it will return to 000. So that means it will count from 0 to 7. Okay, and it's shown here as well. So this is your least significant q0, most significant q2, and to the power 0, to the power 1, to the power 2 position. So it will count from 000 to 111, then it goes to 000 again, right? So it means after first pulse it will be 001, second 010, third 011, and after 7 111, something like that, right? Once we know the counting sequence, so we can get the state transition diagram. Another way to show how the state of flip-flop change with applied clock pulse is to use a state transition diagram. So after each clock pulse, how the states are changing in the flip-flop. So if you want to show it in terms of diagram, that kind of diagram is called state transition diagram. Each circle represents one possible state, as indicated by the binary number inside the circle. For example, the circle containing the number 100 represents the 100 state where Q0 is 0, Q1 is 0, Q2 is 1. The arrow connecting one circle to another show how one state changes to another as the clock pulse is applied. Whenever clock pulse is applied, the actually state changes to the current state to the next state. By looking at a particular state circle, we can see which state precedes it and which state follows it. For example, looking at 000 state, we see that the state is reached whenever the counter is in 1-on-1 state, like when a clock pulse is applied. Likewise, if we say 000 state is followed by 001 state. Let's look at here for 3-bit counter. State transition diagram will be something like that: 000, 0001, 010, 011, 100, 101, 110, 111, again 000. But we already discussed actually how you got it. So this is called state, this is called the previous state, this is called next state, and this is called current state, right? So from the state transition diagram, you know before what is the state before 000 state. You also know what will be the state after 000 state, like 001, right? So this kind of information you will get it from the state transition diagram. Okay, so the concept of mod number is very important. Like you have 3 flip-flop, that means it will count, it will have 2 to the power 3 8 state. It will count 2 to the power 8 minus 1 7 0 to 7, that means 0 0 0 to 1 1 1. So it would refer to mod it counter, where mod number indicates the number of state. So you have 8 state, that means mod it counter. For 4 flip-flop, you will have 2 to the power 4 16 state. So number of state will be number of counter, that means you will have mod 16 counter. So in general, if n flip-flop are connected in arrangement, the counter will have 2 to the power n different state. So the mod number is 2 to the power n. It will be capable of counting 2 to the power n minus 1 from starting from 0. The mod number of a counter also indicates the frequency division obtained from the last flip-flop. For instance, a 4-bit counter has 4 flip-flop, each representing one binary digit. So it's called mod 2 to the power 4 equals mod 16. So it can count to the power 16 minus 1 up to 15, 0 to 15. It can also be used to divide the input pulse frequency by a factor of 16, mod number. Okay. So input frequency divided by mod number. So to determine the frequency factor, right? We will discuss it in the next lecture actually, how you can calculate this kind of frequency.